Hello everyone. So this video is an introductory video to understand how ML models work in a beginner level. Uh, what we will do in this video is we are going to code our own neural network from scratch that will able to detect uh, spam in a piece of text or not. So let's say if email contain a piece of text, we can classify it if it is a spam or not. So for that, we are going to code our own model. So along the way, we will see what are the uh, concepts that are used in that. We will understand the intuition behind it, and you will get a basic background how actually a model works in that way. So we are already aware what problem machine learning can solve, which cannot be solved using the traditional example, traditional programming. So I've taken an example over here. So if we just quickly see, if let's say our task is to recognize handwritten digits, using traditional programming, it will be very difficult. There has to be n number of condition for each case, for each pixel pattern, but still we are going to miss some of these. Similarly, the example we are going to take, which is spam detection. If we do it with the traditional programming, we have to take into account multiple combination of the words, the keywords that are there in that, and still if a new pattern or new things came, then our code might miss it. So we will see how we will utilize machine learning to solve these things. If we see the code that we are going to do, this is basically a code. This we will have a bunch of sentences. This is so we will see both the codes. Uh, One is training one example at a time. Another is feeding a batch of examples, batch of set of emails, and then training the model. We will see both and advantage and disadvantage of those. Uh, so here, if I give you a brief gist, what happening is the sentence is coming in this function train on example, number of iteration we are going to train. Okay, so this is the core logic. We will see what's going on here. We will see all the concept behind it and connect it with our code. So this is basically a forward propagation. Network is assigning the value to each layer, and then this is calculating the loss. After that, gradient is used, then backpropagation to correct the backward layers, and then weight are modified. So we will it might sound some intimidating a little bit, but we will, as we unfold it and we will understand the concept, it will have more clarity. So then, what we are going to cover in this is how the neural network are formed. What is basically a neuron? How the network is structured? What are the weight and biases in it? Uh, as well as the forward propagation, how the new layer activation values are assigned. So we will see first the structure of a neural network, then we will see what is a loss function. It so it basically is how the predicted value is different from the actual value, the actual result that we would have gotten. So this helps. This is a very critical thing. It helps us in training the model and correcting itself. So gradient descent, then we will see gradient descent. So the purpose of the gradient descent is to minimize this loss that we are seeing. So the loss is average of all. We will go in more detail, but I'm just giving you a brief. So this is used to minimize the loss. Uh, okay, then back propagation concept. We will understand the calculus, the logic behind it, and how the error is propagated to the backward layer of the neural network. And finally, we will connect all these things, all the logic that we have seen, all the concept to our code. Okay, so let's start with first thing, how the neural network is structured. Okay, let's start with understanding what neural network is. So in a neural network, the fundamental entity is a neuron. Okay, so the inspiration that is derived similar to the neuron that are there in the brain. So in the brain uh, mul- there are like billions of neurons which are interconnected, and when some event happen in the outside world, these neurons fire up. Not all the neuron, but whatever the relevant neuron are there, those fire up. Uh, so similarly, in the artificial neural network, the neuron are there which are connected to multiple other neuron. So that is the structure of a neuron. Okay, so how this value is determined of a neuron? Okay, so this value is of a neuron, which we can say is the activation value, which is between 0 and 1, is determined by all the neuron that this particular neuron is connected with. Okay, so whichever neuron has a strong connection will have a more influence. Okay, that is one thing. Or another is, even if the connection is smaller, other neuron is firing at a bright, it has a higher activation, then also it will influence this neuron. So there is a term known as the neuron that are fired together, wire together. Similarly, if some neuron has a higher activation, it will have a more influence on another neuron, and it will also have a higher activation. So that's how a neuron is represented. Interconnection of multiple other neuron. So how now the next part is how the value of this neuron is determined. So it is the sum of all the activation multiplied by the influence, which is basically a weight. Activation is the value of the previous neuron. Weight is how much influence this any neuron has on this value of this. Okay, this is the weight. So this is a multiplication of both these, all the neuron that are connected, plus some additional bias is added, which help us to if let's say certain neuron is getting overactivated, so we can reduce that activation value if that much activation level is not needed to normalize this. This bias is added. So and then uh, because the value is between 0 and 1. Okay, so to convert it between 0 and 1, this value can be a some any value 40, 50, 80, 800, minus 10. It can have be any value. So between 0 and 10, what we will do is we will pass it via sigmoid function. Sigmoid function is a special function. So what it will do is it will convert the higher value tend towards 1, and lower the value it tends towards 0. So between 0 and 1 is the range, and in between is a zero point 0.5. Okay. So if we see the role of bias is, let's say this value came out to be 3. Okay. And our bias is negative 3. So it has significant, so without bias, the value would be 3. So it will more towards 0.8 or 9. But the bias bias minus 3 has significantly, we can say, deactivated this value, and it came out to be zero point 0.5 instead of 0.8. So that is the use of bias. So these two are the parameters. Uh, Weight are the parameter and bias are the parameter that determine the final value of a neuron. It will based on this new activation value is calculated, and similarly this will be connected to other neurons in further layer. So that value is calculated based on that as well. Okay, so we have understand weights and bias. So now the neurons are arranged in a layered network. So one layer, there is this one layer, then this is another layer. So in the second layer, or each neuron is connected to every other neuron. Okay, every other neuron, and then this neuron is connected to every other neuron. Based on that, this value is determined, and each connection will have some weight. Each connection will have some weight. So this layer network allow us to uh, identify the pattern, and based on the weight those connection will be formed. Okay, so if we will see in our code, this for the spam detection, it will have 12 input neurons because we have taken a vocabulary of 12 words only. Ideal, this is a small example, but it can have uh, thousands of words. Okay, so for simplicity, we have taken 12 words. So these are the 12 words that we have taken. So to feed this input, what we will do, this, let's say this is the sentence. We will do is we will vectorize this sentence uh, to uh, based on the vocabulary. So whichever words exist, that neuron will be fired up. Okay, so if we will see this action exists, this neuron will have a value of 1. This account exists, this will value of 1. Count is there. And then we have urgent is there, verified is there. So in that way, those particular neuron, input neuron will be fired up and we will vectorize this sentence and fed it to the neural network. So if we will see how many parameters this network will have, we can calculate that as well. This particular neuron, okay, in the second layer is connected to 12 neuron in the input layer. So there are 5 neuron, 12 into 5 is the connection, is the number of weights uh, is there. These are the weights parameter. And then these 5 will have a 5 bias. And for the output value, this 5 will be connected, are connected to 1 and plus there is 1 bias. Okay, so total neuron come out to be 65, something like 71. Is the total, sorry, neuron I am mistaken. Total number of parameters that this neural network have. Okay, and if we will see in this one, so this is another neural network that is used for the first example that we have seen for the image detection. So how the data is fed into this. So how we will vectorize this image. So we what we will do is we will whatever the handwritten digit is there, we will convert it into a 28 by 28 pixel value, and every pixel will have some value. Okay, so these all pixels, if we will see, these all pixels are zero, but uh, these pixels are fully bright, and these pixels that are on the edges have very less value. Okay, because these are not fully bright. So we will take a 784 array, which 28 by 28 array, one dimension vector. Okay, and then feed that the value, whatever the value of that vector to the neural network 784. Okay, and based on this weight and bias, this second layer value is calculated, and similarly the final value will be there. But initially the weights are random. Okay, so bias are random, so it doesn't make any sense. Now, if we will see how much parameter this neural network has, so this come out to be uh, 784 is in the initial layer, and each next layer is something like 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 neuron. Okay, each neuron is connected to 784. Okay, plus and then plus is 16 are the bytes. Okay, that is first term. These are the number of weights plus bytes. Then 16 plus 16 plus 16. That is the next layer. And final layer is 16 into 10 plus 10 by. So this come out to be 13,000 something. These are the number of parameters that this neural network have. So all our effort in the neural network is to get the optimal value of this weight and bias so that network will able to predict the correct value of the output that we are expecting. Okay, here it will assign the probability to each number. It can have probability 0.1, 0.2, 0.8. The higher the probability towards a number, the more the network is suggesting that this could be our number. So there are 13,000 parameter to be optimized in this. It has only 71 parameter to be optimized. So then this is how neural network is. Okay. So now let's see what is a forward propagation.
Forward propagation is nothing, just getting the value of each neuron, determine the value of each neuron based on just what now we have discussed, based on the activation weights and bias of the previous layer. Okay. So these value we can determine this value because this is connected to every other neuron we can determine. So this is the first part of our network. So if we will go in the code, we will see here uh, this is our uh, layer one. Okay. So these are the weights. Okay. This is the layer zero. So what we are doing is we are taking the sigmoid, okay, and layer or end weights multiplying by the layer zero will have the activation value, okay, and the next neuron so bias we have ignored for now. For this example, bias can also be there, but it is simply a dot product. Layer zero will be a product. This will be a vector like this, okay, and then weights will be a vector like this, because each neuron has n number of weights because it is connected to other neurons, all the neurons in the previous layer. So this value will got multiplied and give us the uh, layer one value of which will be again a vector of 16 or whatever 5 if we have taken the if we are considering in this spam example, it will be a vector of 5, and eventually layer 2 will be a vector of 1 value. Okay. So to get the layer 2, we will use layer 1 and then multiply it by the weights. So this we will see at the time of dry run, and layer 2 will get the value as well.
So, in the last part, we have covered what a neural network is, what are the weight and biases. Then we saw briefly what forward propagation is. So, I have taken the example from our code to understand it more clearly. So, the forward propagation, as we have already discussed, is getting the activation values of the further layers. So, how we will get it is we know this activation value will be a sigmoid function of summation of all the weight multiplied by the activation values of the previous layer. So what we have taken, this is the first layer. Okay, here. This is a 12 neuron represented here. Then the next layer is a 5 neuron. So to get the value of the next layer, we will do a dot product with the weights. Why we are doing the dot product? Because so if we see this weight array, this has a 5 neuron, and each will have some different weight based on the connection it will have to the previous layer. So this is a 12 by 5 matrix. Okay. So what we will do is, because we are interested in W1 A1 plus W2 B2, right? So this value we will get, this summation we will get for each neuron by doing the dot product of this. Hmm. These two matrices. Eventually we will get this layer one. Okay, this is the perspective of forward prediction from the code wise. So this is what we are executing. Okay, so after the forward propagation is done, the next part is is the loss function. Okay, so based on this, the final layer will have some value. Okay, based on the random weights and bias that we have taken initially, it will have some value. Okay, so loss function represent how much this value is deviating from the actual value. Okay, if this has a y actual, and which is, let's say, that the correct value is 1, and our model is predicting 0.3, so this deviation is 0.7. This is our loss. Okay, so there are multiple ways to calculate this loss. Okay, in which we can tell the model to how much it is deviating. So the few ways we can calculate this loss is mean absolute error, which is simply y actual minus y predicted. Then is a mean squared error, which we are going to use. So the advantage of this is if there is a small error, okay, that will not be highlighted that much. If the error is 0.1,
Okay, which is basically, let's say the model is predicted zero point 0.9 and actual value is 1. So the difference is zero point 0.1. When we square it, so our actual error that we are telling the model is 0.01. Okay, so that is reduced from this value, actual value. Okay, but if it is a higher value, then it will be more highlighted. Let's say error is zero point 0.9, then it will be 0.81. Okay, so that is one of the reason we can say we have taken the square loss function. Okay, so the loss function we have seen. So this loss function is taken not for the single example, but average of all the example that we are feeding to the network, because single example may have proper result. Okay, due to some probability, it may have proper result. So we cannot conclusive say based on a single example. Uh, we have to feed n number of example in this and take an average to see how much actually the cost function is deviating from the actual value, right? So this will that will give us a clear picture. So if we will see, this is how it is represented, and this is eventually a function of weight and biases. This is dependent on weight and biases, and our goal is to reduce this cost function. During the whole training part, the goal will be to reduce this cost function to minima. So it will be the minima is zero. Zero, we won't have any error in the mod in the model. The model is predicting absolute correctly the whatever the input we are feeding into the model. So that is the goal. Okay, so if we will expand this, this will come out to be this one, right? And then it is dependent on the activation value of this, and then this value is further dependent on the weight and the activation value of the previous layer. So if we will see this yi minus sigmoid of z, this is the z, and then this z value is basically summation of weights and the activation value weights. So this is the weight, this is the 5 neuron, the summation of weights and the activation value of the previous layer. Previous layer again is dependent on the layer before that. So we will see this is again the sigmoid because activation. This there are 12 to weight into actual value plus this is a simple example to get understanding how the cost function is dependent on weight and biases. Okay. So eventually our goal will be to get the optimal value of weight and biases so that cost function will be at its minima. Will be at its minima. How we will do that? We will understand that in the part of gradient descent. Okay, so last time we have discussed up to the loss function. So we have discussed the cost function. We have calculated it, how it is dependent on weight and biases. So we established that the cost function, which is final loss function, is a function of weight and biases, and any change in the weight and biases of the value of the network will going to change the cost function. And the goal of the training of a neural network is to reduce this cost function. Okay. And in reducing this cost function, the gradient came into picture. Okay. So this is basically a gradient. It is a rate of change of cost with respect to every weight and bias. This is also called a slope. Okay. So we are going to understand what this gradient is and how rate of change is going to minimize this. Okay. So let's come to the gradient descent part. So if let's say we take a function, okay, y is equal to x square. Okay. So now if we will take the slope of this with respect to x, dy by dx is equal to 2x. Okay. So this is the gradient of this function.
Okay, what does it tell? It tell us if where are we, wherever we are standing. Let's say x is positive here, x is 2. Okay, so then the gradient will be 4. So this tell us on increasing of x is increasing. Okay, then y will also going to be increase. So this is the slope. So here the slope is positive. Okay. So when the x is increasing, y is going to be increased. If we are standing over here -2, okay, then this value will be -4. Okay, then the slope will be this one. This is a negative slope. So this is telling us when we are going to increase x, then y is going to be decreased. Okay, so that's what it tells us. Uh, so if we will see, this is somewhat similar to our cost function. Okay, so what it we if we want to reach the minima. So this tell us how do we modify the value of x so such that this tell us the direction in which we move so that y should be at its minimum. We reach the minimum. How do we reach it? Let's say we are standing here. So this tells us the slope is negative. Okay. So you move in this direction. If you increase the x, y will going to decrease. Let's say if we are standing over here. Okay. So now this tells us the slope is positive. Then we have to move in this direction. In increasing x will increase the y, but opposite direction will reduce the y. So both the things are important, the sign as well as the magnitude. So higher the magnitude, higher is the slope is decreasing at a higher rate. So we can take a large steps. But the lower the slope, okay, here the slope is lower. So at this place, the descent is much less. So the step will be smaller. Okay. Here we can take this step, then step will be smaller going forward. So this tell us the direction in which we should move. Okay, so how we will calculate the x? We will modify x. This is the learning rate. This is the gradient. So we see it higher the slope, higher is the movement we are going to take. And learning rate is an arbitrary value which we will take to speedify the process. This is a factor, or uh, speedify if it is a more than one, we are speedifying. If it is less than 1, 0.01, then we are uh, reducing the piece at which reducing the step. So it is a fixed value, and it this value changes as we take the further step. Okay, so here some context you might have gotten how this help us in reducing the value of y. This is just a basic math, 11 12th math. Then let's extend this concept to the 2D plane. Okay, so let's say our parabola is x square and z square in a 2D plane. So this is our parabola. Okay, this is basically a shape of a bowl. So here the gradient come out to be at any point wherever we are standing. Dy by dx, it is a partial derivative of both. Okay, so this value. So whatever the value of this game, based on that, we will take the decision if we want to minimize the y, in which direction we should move the value of x and y so that we move towards the bottom of the pit. Okay. So here this will be a resultant of these two vectors. Okay. So wherever we are standing, let's say one vector is telling it to move us to move here, then we will move in this direction. Okay, so this is a resultant. So this we have visualized in a 2D plane, but actually our cost function is going to be a n dimension plane, which we cannot visualize like this, but the concept extend in this way only. So there will be n number of weights it will be dependent on W2, and all that constitute this gradient vector, and we will going to minimize it and move all the values in the direction in which the gradient is telling us to move. Okay, so this is for 2D plane. Let's do a simple linear regression example as well. See, to solidify our understanding. So I have taken this example. This is a beginner initial example that is taken. So let's say we have this equation y is equal to mx plus c, similar to our equation which we have w a plus b, that equation that we have. Okay, which is the value of z. So let's say we have this equation, and what we want is we have some test value. X is equal to 1, then y is equal to 3. X is equal to 2, then y is equal to 5. Then similarly. So our goal is to predict the value of m and c such that this equation fit in these value, and if a new value came, it is going to predict it. Okay, so let's see how we will use a gradient to help with this. Okay, initially, similar to weight and bias, we will use some random value of m and c. So these are the random value that we have taken. So if we put this, we will get the value of x as 0.5. Okay, with first set, second set we will get 1, and third set we will get 0.5. Right? We have put these random value. We don't know the actual value. So, but this is deviating from the actual value is 3. This is 5. This is deviating from the actual value. And then this is 1, this is 5. Similarly, this one. So, if we will calculate the loss that we are having in this, the total loss, which is basically average of a mean square average, so which is this one. So for point 1, if we will see, the error is 3 minus 0.5, this value, 5 minus 1, 16. Okay. Similarly, 30.25. So if we will take the average of this, it came out to be 17.5. It is a higher loss, very high loss. Okay. So our goal is to minimize this. If we are going to minimize it, we are moving in the right direction. So how do we do that? We will take the gradient, which will tell us in which direction we should move. So this is dc by dm. It will came out to be this. If we partial derivate it with respect to m, you can do it. It will came out to be this only. Then if we will do uh, dc by dc, it will came out to be this value. Okay. So then what we will do is we will calculate these values based on the value of m and losses that we are getting, right? So if we will calculate the first term, the error is this part. The error is 3 minus 0.5. Okay, this is the error. Okay, x value is first is 1. So this value will be minus 2 into 2.5, 1 minus 5, and this value is this one. Similarly, we have calculated for the next set minus 16, and the next set minus 11 and minus 33. So if we will average it out to calculate the total average gradient, it's come out to be minus 18, and it is come out to be minus 8. Minus 18. So this is telling us if we so the similar to the parabola example where we are standing here. So we have to move in the opposite direction to reduce the loss. Okay. So what we will do is uh, we will apply the similar thing. The learning rate we have taken 0.01, and the gradient we are getting 0.18. So what we will get is 0.68 is the new m. If we would have taken learning rate as 0.1, then we will get value as 2.3. Okay, so similarly, the value of C is 0.8. If we would have taken as learning rate as 0.8, if 0.1, then it will be 0.8. So what we will see is, so actual equation, if I tell you, is y is equal to 2x plus 1. So we are converging, we are moving towards this value. Our m is moving towards this, our c is moving towards this. Okay, if we have taken a higher learning rate, higher jumps, then we would have landed 2.3 farther than this value. Okay, and similarly 0.8. So now, if we will feed these new values of M and C again into this iteration, into this loop, then calculate the cost function, and similarly, then again we have to calculate the gradient. Then we will find out we will be much closer to the actual value. And the more this iteration we will repeat. So if we will calculate the loss with the new value, it came out to be 13. So it has been lower than 17, which we are already getting. So this is how the gradient descent will help us to select the direction in which we must move in order to reduce the loss. Okay. So in the next video, we will understand this calculus of calculating this partial derivative, and how, so this we can calculate dc by dw, but how this loss is and this as well, this we will find out using the calculus, how this loss is propagated to the backward layer. So here it will be dc by d w3 w4 like that, all these layers, how this loss is propagated and how that value is calculated. So that we will see, because once we have the gradient, we can tweak the value. So here, if we will see in the code, which we have seen initially, so this is the logic that we are doing. This is the weight, this is the learning rate, and this is the uh, gradient that we are seeing over here, this one. So we are multiplying the learning rate with the gradient and changing the weight. This is how it is working here. So this gradient part we have understood, but now the next part that we are going to understand is the back propagation part, how this layer 2 delta is getting calculated coming from. Uh, okay, so that we will see in back propagation part. Part we will see what is back propagation. So earlier we see what gradient is, and we need to compute the gradient of a cost function with respect to every weight and bias to effectively optimize it. Okay. So back propagation is an algorithm that help us in that process to compute the gradient with respect to each weight and bias of a network. With the help of this, when we know the loss or error for the outer layer, we propagate it back to the inner layer, so that we can compute the gradient of those layer as well. Okay, so back propagation is based on the chain rule. So it uses chain rule, not based on. So first we will, let's understand what chain rule of the of calculus is. Then we will see the calculus part of back propagation after that. So chain rule basically says if a function y is depend on u, okay, and then u again in turn depend on function x. Then if we want to find the derivative of u with respect to x, okay, so if we see u is not directly dependent of x, u is dependent on u, sorry, y is not directly dependent on x, is depend on u, and then u depend on x. So what we will do, we can found that derivative by multiplying y with respect to u. We will first do y with respect to u, and then derivative of u with respect to x. That's how it is. So if we want to find the derivative of a function which again dependent on another function, we will do we find the derivative of function with respect to gx, and then gx with respect to x. That's how the chain rule works. Okay, so how so to understand this calculus part, we will take a part of our neural network, a three neuron system. This is the output layer. This is the middle layer, which we have in our neural network. Our neural network also have three layers, first, second, and third. It can have more than three or n number of layers, but the same logic applies to that as well. Okay. So we have taken this part of our neural network. This AL is the activation value of the final layer. Activation value is sigmoid of ZL. This is ZL. Then Z value is a function of WA plus B, which is WL. Okay. Previous layer activation plus if there is a bias, then this is. Okay. Similarly, previous ZL, this is the activation of this layer ZL. This is a function of value, whatever X value is there, X into WL plus B. Uh, so that way, this simple part of a network is. So if we will see the final cost function, which is there, okay, it is a part of the activation value because the cost function is basically the square of this value, uh, final value which network is given, then actual value. So it is a function of this activation. Okay, then this activation value is a function of z by sigmoid z. Okay, and then this z is a function of w. So we are interested in this part, gradient of cost with respect to W. So as per chain rule, this is not a direct function, but a nested dependency. So we will apply our chain rule, derivative of cost function with respect to activation, then derivative of activation value with respect to Z value and derivative of Z with respect to W. Okay, so we will calculate all these part and then we will try to get this gradient of the last layer. Okay, this is pretty straightforward. So what we will do is this is our cost function. We will partially derivate it with respect to activation, which we are interested in, which is to this came out to be this value. Simple derivation is there. And then we will do the find the partial derivative of activation value with respect to z. When we do that, this simply come out to be a derivative of sigmoid function into zl. So for better understanding, I have elaborated here. D by dz it is a derivative. This is our z sigmoid function. Okay, when we do the derivative, it's come out to be this value. So this is this value. And if we write this in terms of original sigmoid function, it came out to be this one. Okay. So this is the value that we eventually get, the derivative of sigmoid function. Okay, then we have the z value. We will derivate it with respect to weight. So when we do that, this term will vanish. Okay, this is a multiplication. So W derivative of W will be 1 and this value will be there. So this is the value. Okay. So if we put all these value that we have get it by doing the partial derivation, we what we will get is this value. Okay. Activation multiplied by this value. This is the sigmoid derivative and this is the cost function. So if we see uh, the cost function rate of change of cost with respect to activation dependent of how far our value is, right? How far our value is. If model is predicting the correct value, so this value is 0. So then we have this complete term, and similarly, this is the gradient we get, and for with respect to bias, if we want to see, we will get this value because the derivative of z with respect to b is 1. It is 1. So we get this value. So if we will see this term is common in both. Okay, this term is common. Then if we uh, if we quantify this term, this is delta L. We segregate this term, and which is this value. This is an important factor. We see as we see how error propagating backward, but this is very important factor, and this is nothing but the gradient of cost function or the derivative of cost function with respect to z value. Z consists of both weight and activation of previous layer and bias is combined. Okay, how the cost is changing when we change the value of z. Okay, of this neuron. So this is basically that thing. Okay, how sensitive the cost is with respect to z. That value it signifies. Okay, so this is that part. If we will see these two part is there. So how it is because C is a function of activation. Okay, and activation is a function of Z, simply which we have discussed. So that's how this we can see the same thing here. Then we if we represent it in terms of delta L, we can see the gradient is activation of uh, uh, L uh, minus 1 into delta L, and similarly this one. Okay, so this is for last layer gradient, but let's see how we will calculate now the next part, how we will calculate the gradient of cost function with respect to the weights of previous layer, this one L minus 1, how we will calculate it. So if we will see, the cost function doesn't have a direct dependency on weight of previous layers, but it is indirectly dependent. So the chain here is longer. Okay, so how we will see how trace this dependency. So we will see the cost function is dependent of activation of the last layer. Okay, so this activation depend as we see is a function of Z, sigmoid Z. Then this is a function of activation of last layer W A L minus 1 plus B. This is a function of activation of previous layer. Then this activation is a function of Z value of that layer, and that Z value is a function of weight. So this is the chain which is we are going to derivate. So if we do apply the chain rule and do the derivation with respect to previous layer, so this is how our derivative will come out to be. You can check it. It is the same thing. Derivative of C first with respect to AL and then EL with ZL. ZL is the same thing eventually. Okay. So if we start calculating these value, we will see the derivative of ZL with respect to WL. Okay, is nothing but E activation L minus 2 because Z L minus 1 is equal to W L minus 1 A L minus 2 plus B. Okay, so when we do the derivative partial derivative, this term cancel out and this will be 1 and this will be L minus 2 only, that will be left. So this is the value. Similarly, what we have seen this term, okay, a derivative of activation, which is nothing but the derivative sigmoid derivative into ZL minus 1. Now, this value, derivative of ZL minus 1 with respect to activation is WL. How? Because ZL is WL, right? Into activation of previous layer. So when we do the derivative, it came out to be this. So, and these two terms is from the first layer. Okay. So if we will see now here the linkage will come. So these two term which the value of these two term if we will see these two are the terms that we are in consideration is nothing but delta L, which is our error sensitivity or a delta layer error delta we can say is this term. Okay. So here this is delta L. So if we combine these two, all these things, our value come out to be this uh, come out to be before that it come out to be AL minus 2
and delta L minus 1. So how, so this is the main part. So here this delta L minus 1 of the previous layer will be this value. Okay, this what we have got from here, okay, into WL into, so what we are just doing, we are just combining these terms. Okay, delta L into WL into this part. All these when multiplied come out to be this value. Okay, and we haven't multiplied with the activation yet. Okay, so when we multiply it with activation, this is the term that is there, the similar that we have seen before. So this term is a error sensitivity of the previous layer. This is the factor that we are multiplying the activation value with. Okay, so this is the factor that we are, and this value we calculate based on the weight and this delta L of the previous layer. So this is how the error is getting propagated backward. Okay, so now we can calculate the gradient. Okay, when we know the delta L of the previous layer. Similarly, this one. Okay, this is the, we can say, all that is in back propagation. Similarly, if we have to calculate L minus 2, we can use sigmoid derivative of Z L minus 2. Okay, and then WL minus 1 and delta L minus 1, which we already know by when we calculate of the previous layer. So error sensitivity of previous layer can be calculated. This part, so this is also the error sensitivity which we have previously discussed with respect to ZL. So ZL is nothing but if we expand this derivative using the chain rule, it came out to be this value. And this term, this is the term that is for the last layer, the layer after this, and which is basically this one. So that is here in backpropagation. So we see the error signal flow is delta L we have got for the first layer. We multiply it by WL, okay, and multiply it, and then then propagate it backward, and then multiply it with sigmoid derivative of this value to get the gradient of uh, or the loss density of this layer. To get the gradient, we will multiply it with the activation. So we see how we in this we can get gradient and bias for every layer with respect to every parameter that is there in the network. So in the next part, we will relate this understanding with our actual code, how these terms, how this in logic and intuition fit in with our code. Okay, so now that we have the understanding of neural networks, as well as we have seen the gradient descent, and just now we see the calculus part of backpropagation and how it helps in calculating the gradient of the backward layer. Let's move to our example that we have taken initially, the spam detection one, this one, and see how we can apply all those things. We will understand it step by step. So how those things help to code and as well as train this neural network that we have taken. So this is a simple example. What we have taken, what we are doing here is we will have a bunch of sentences uh, uh, which we are training the model on to identify if the sentence is a spam or not. So the process will be initially we will tell the neural network if that particular sentence is a kind of spam or not. After we have done the sufficient training, if a new sentence came, based on that training, the model will able to predict if that sentence is a probable spam or not. So if you will see here, these are the sentence initially we are training on the model. Then we feed these two examples. Okay, and then we will see how model is predicting these values. Okay, after that, what we are doing is we feed two more examples with the value that is it's spam, this is not spam, and then we will see how our prediction now fares. Right, so this is the process going to be. Okay,
If we will visualize this neural network, which we have already seen, this neural network will some look like this one. Okay. So what we are doing is, uh, when we feed a sentence, we will first convert into the vocabulary, transform it to the vocabulary vector to feed the sentence. So vocabulary, I have taken it as a 12 word here, but this can be thousands of words. So the sentence will be converted into this vocabulary, which is a vector. So here the conversion is there. So if you will see, this is the example that we are taking urgent action required verify your account. So action is there in our vocabulary. So this is highlighted, then this account is there. This is also highlighted, but other value are zero. This is not activated. Urgent is there and verify is there, as well as your is there. So these value are highlighted. So this is our first layer of the neural network, right? So after the first layer, what we will do is a forward propagation. This value, the weight and bias will be initially random, which we can see over here. The weights is taken as random, and then the weight of second layer is also taken as a random matrix. So this matrix is a 12 by 5, because is mapped to each has a weight respect to every other neuron in this layer. So this is the weight and a random weight metric. So if we, let's say, now visualize this and put the breakpoint over here. First, let's put the breakpoint over here. So yeah, it is here now. So the weights first one. One second, the weight 0. So this is a 12 by 5 matrix. Each neuron, this is the 0th neuron, has weight mapped to all other neuron in the previous layer that we can see over here. Okay. And now this is the weight. Now let's move ahead. Where is our, uh, let's move ahead. Now we are here. Now it is sentence is converted to vector. So if we view as array, this is our initial layer, right? And then it's just changing the structure. It's into a column row, just to simplify the multiplication. So now if we will see the result, okay, this is the result that we have. This is the actual value, which is 1, right? Now we will start the training. This is the number of iteration that we are going to train the network on. We are going to train this example on 5,000 iteration. So let's move ahead. Let's see the first step. So the layer one is calculated. The layer one is this first one. This is the first layer. This activation value are calculated using the forward propagation, multiplying the weight by this activation value. The same we are doing here. This is a dot product of layer as well as the weight, and passing it then by the sigmoid function to normalize it, which are the same we have seen, right? Now the layer 2 values of this is the layer 1. Layer 2 is the our final value. So the prediction come about to be 0.46, which is 10. This is a random value that has came up. This is leaning toward not a spam, whereas actually this is a spam. Y value is 1. So what we will do, we will find out the loss error last layer we have find out. This is the last layer error. Okay, after that, the next step is what we will do is we will calculate this delta, okay, delta L, which is this loss multiplied by the sigmoid derivative, which we have seen over here. This is the delta L, right? See, this is the sigmoid and multiplied by this loss. The same we are doing over here. Layer 2 delta we are calculating. Okay, and then what we will do is layer one error we will calculate. Layer two error, this is just simply y2 minus y minus layer two. So now this is the back propagation part. So back propagation in the back propagation, what we are doing is to calculate the layer one error. Okay, so what we are doing is we haven't multiplied with activation yet. We are just calculating delta of the previous layers. Okay, so we multiply weight into delta. So that is this step here. You recall, this is the previous layer delta. This is multiplied by weight into L, and then we will multiply by the sigmoid function. If you will see, this is the sigmoid function, and this is the value of the layer 1 error, which is weight into previous layer delta. Right. Hope you have got this part. This is just simply the representation of backpropagation that we have done over here. We first calculate, I am reiterating it, we first calculate the delta L. Okay, this will help us to calculate the error in delta of the previous layer. So first, this delta L is find out 2 is not needed. So this will be taken care as the number of iteration is very higher. So that part will be taken into that. Just simply the error we have multiplied by the sigmoid derivative. After that, we multiply by the weight in the next part, which we see over here. Okay, this is the weight. Now, to calculate the delta of the previous, this is layer. This is called layer error. Well, we can call it anything. This is the layer delta of the previous layer. So this is layer 1 error into the sigmoid derivative. This is the whole term. Okay. So now we have got the delta L of this layer and delta L minus 1 of the previous layer. So we can multiply these value with the weights. Okay, to get the gradient of each. So same thing we are doing. To get the gradient, we are multiplying by the activation value. Okay, the same if we will see, to get the gradient respect to particular weight, we are multiplying with the activation value. So the same thing we are doing over here. Transform is just to help with the multiplication part. It is a column array, it will convert it to the row. So layer 1, these are all the activation value and multiplied by the delta. So one more thing here, we have taken sigmoid derivative. So sigmoid derivative is just x 1 minus x, which we have seen previously. So x is the activation value that we are feeding, which is itself a, so if I show you here, this came from here, this part, this part. So this is the sigmoid derivative that we are taking. So then the value of b we have not taken to simplify it, reduce the complexity, but bias we can also take, but here only the weight are considered. So now what we will doing, we are taking a arbitrary learning rate. So this, as we have seen, this is how fast or how slow we want to move towards that gradient. Okay. So learning rate is default one. This is the gradient. So the weights will get updated based on the gradient. Now these weights are again fed into the system, and again this process will repeat multiple times to get the proper weight and biases. Again, the next example it is trained on. So and so in this, if we will see, we are training the network one example at a time. Okay, we feed one example, then train on that. We feed another example. So there are certain advantage and disadvantage to this thing. So there is another technique in which we feed multiple example at a time. So as we have seen previously, the cost is basically the average of all the example that are there. Okay, one example we can take, but the disadvantage is our gradient movement is bit more erratic rather than getting smooth, because one example can point it to the different direction, but another example can point to different direction. So we may not reach the exact minima with the single example, but if we take, let's say, n number, all we feed all the emails or all these sentences in a network at a time, in a single iteration, here one example. then the gradient will be much more smooth, and we can converge to the minima at a faster rate. But problem is that this multiple one is a computationally as well as memory expensive, because here all the training examples have to be in the memory. Apart from that, all the multiplication has to be done in the same time. So there are GPU which makes it more efficient by parallelly multiplying it, but that is the thing that we can keep into mind. Basically, the multiple one, the gradient is much more smooth. Here, the descent is noisy. It is not that much smooth. The variance is higher. So that is the thing about single and multiple training part. So now when we run this program, let's run it. So okay. So now we have run the training on first, second, third. Training finished on four example, right? So then we can see now when we feed this example, the model is predicting spam probability as 0.46, which is not correct still, even after training four example. Right. And now when we for this example, this is very much accurate, but for this is not. Now we train on two more examples. After training, we can see the spam probability has increased to 0.78. So this is we can see the more we training, the spam probability is increasing. So if we will visualize this, this is our network. Okay, for single example. We will cover the multiple as well. This it is similar, just new nodes, not nodes, but parallel nodes we can say will be there for other examples. So here, if we will see, this is the example we are feeding. Let's take one iteration. Average error is 0.5, which is much higher. Okay. So these weights and these weights values are random. Right, as we keep on, let's train for the 100 example, so we can see the average error has reduced a considerable bit, right? And the spam probability is also 0.93. If we keep on training, the spam probability is increasing. Okay. So if we will do that, this is 0.96, this is not a spam. So now the network is predicting, right? So that's how the single one work. Uh, you have the understanding. Now, if we will see quickly the multiple one, in multiple one, what we will do, we will take the sentence array. Okay, and all these example are fed into the network at once. So if I put the breakpoint over here and we will debug it. So layer 0 earlier was a single row with 12 vector, but here it will be a 4 by 12 because four examples are there. So if we will see let's move it forward, layer 0. Okay. So now we will see 0, 1, 2, 3, 4 example and four rows, different four rows. So all these four rows contributed to the loss function. If we will see over here, this is the layer 2 error. Okay. This some in this as well, the dimension has been increased for the first example, second and third, fourth. Uh, right. Just that one extra dimension has been increases for the example uh, in every parameter. Similarly, delta is created and the weights are training. So if we will see this neural network, how it is performing. So what we have done is we have taken this four example. Okay, their probability earlier was coming out to be 0.46, right? With the four example one at a time. Let's see how this example is doing. Let's remove this and close this as well. This is our final value. So we can see initially the error is 0.51. As we keep on increasing the iteration, the network is getting much more optimized. The error has been fairly reduced. Now, here, if we will see, this is a difference. So the spam probability on this 4 training only came out to be zero point 0.6. Okay. And this is zero point 0.0. So this is getting first the higher probability. And if we train the network more on iteration, then there is a chance that this will going to increase. Okay. So this is about the neural network. So we have created our own neural network and train it. And with the new example, it is able to predict the spam probability. Hope you have got some understanding and some background how these things work. This is a beginner introduction. Okay, thank you.